In this lecture, we'll learn how to conduct an ANOVA, and we'll go through a calculation of a sample ANOVA just on PowerPoint. We'll have whiteboard demos later. So here is the research question. Are jurors more likely to convict a defendant if they learn the defendant has a criminal record? The experiment goes like this. 15 individuals were given background information about a woman accused of passing bad checks. Then they were shown a DVD of her trial. The background information was identical for everyone except for one piece of information which was randomly varied in the information sheets. So some saw the defendant had a criminal record, some saw the defendant had no criminal record, and some received no information about a criminal record. So you can see we have three conditions, and this is the same example we went through in the first lecture. So here are the data that we've collected. So in these 15 individuals, we had 5 assigned to condition A with a criminal record, and you can see their ratings of guilt. We had 5 assigned to criminal B, where they saw an information sheet that said the defendant had no criminal record, and you can see their ratings of guilt. And then in this last group, we had condition C, 5 individuals, and you can see their ratings of guilt of the defendant. So once again, we have a total of 15 individuals divided into 3 groups with 5 individuals in each group. The process that we're going through here is only appropriate when we have equal size groups, like in this example. The procedure is a little different if the group sizes were unequal, as they usually are, frankly. So in this case, we have 3 populations we're comparing: those who saw that the defendant had a criminal record, those who saw that she had no criminal record, and those who saw nothing at all. The dependent variable is ratings of guilt. One-tailed high is always the tails in the F-test, and our research hypothesis is that the population means are not equal. Our null hypothesis is that they are equal. In steps 2 through 5, we'll finish this example. The steps are the same as we've used earlier so that we understand the process. So first we describe the comparison distribution, and we only describe its shape because we're just looking at this ratio. And we know that, as we looked at before, it's 0 means the the 3 or more group means are exactly equal. The within and between group means, and then it's the skewed distribution showing all these ratios, so they're always positive numbers. They can get quite high in the F distribution, and we're just going to be describing this shape, and it varies depending on the numbers in the samples and the number of groups. And so we have to look up the shape. We'll use the calculator tool that you already saw, the same one we used for the t-test. We'll look up the degrees of freedom between, which is just the number of groups minus 1. In our example, that's going to be 2. We have 3 groups minus 1, so that will be 2. And we'll look up df within, which is the number in the first group minus 1, plus the number in the second group minus 1, plus the number in each of the groups minus 1 from each group. It's the same way we calculated df total in the independent samples t-test. In step 3, we're going to look up the cutoff point, and once again we will be using that tool similar to the same tool we used for t, but we'll have to enter these 2 degrees of freedom. And we're going to base it on alpha 0.05 and, as described earlier, 2 and 12 degrees of freedom. And we find out when we do that F alpha equals 3.89. So we mark it just like we've done before. That's about maybe where the 3.89 would go. And the region that's extreme, further into the tail, is the reject region. The fail to reject region is all the area that's beneath the cutoff point. We calculate the sample F score using the formula MS between divided by MS within, and we'll go through that process on the next slides. And finally, we decide and conclude if the F value is greater than F alpha, we'll reject the null. Next, first we're going to estimate our within groups variance, which is the top number in the, the bottom number that we use for calculating the ratio. We call it EVAR within in our class, variance within, or MS within, mean squares within. So I'll try to be consistent. I think I'll stay with EVAR within, but just so you know, either one is appropriate. So when all groups have equal sample size, all we do is we calculate the sum of squares in EVAR for each group, just like we've done before. EVAR within then is just the sum of all those EVARs for each group divided by the number of groups. Or you could just take the average of all those EVARs that you calculated for the groups. When the n's are not equal, we'd have to use like a pooled variance calculation where we proportionally weight the variance for each sample, just like in the independent samples t-test. We're not going through any examples like that in Excel. So here is a look at this process. You can see here that I'm going to go through this with pencil and paper in another example, but just so you see what it looks like. You can see that we've laid out these data just like we did for the independent samples t-test. Here's each individual score for our condition 1. We went ahead and looked at the number, the degrees of freedom for this group, the mean for this group, the sum of squares. We calculate by calculating the deviations, each score minus the mean, and then squaring those deviations. And our sum of squares is the sum of this column, these squared deviations, which is 18 in this case. And so EVAR is SS divided by DF, and we get 4.5. And when we continue on, we've done the same for these other samples. I didn't type in all of the calculations, but you can just take a look here and see that all we've done is a typical calculation for EVAR for each of these samples. So those are the variances that will serve as the average for our within groups variance. And you can see this formula down here. The EVAR within is just the sum of all these variances divided by the number of groups, which here you can see I've written down all of those EVARs divided by 3, and we end up with 5.333. Next, we're going to estimate the between groups variance, and this really is just like calculating EVAR for the means. So don't overcomplicate it. You'll see how simple it is. So we're just going to find the mean for each group, which we would already have done. And we're going to, of course, do that for each group. Then we're going to calculate the grand mean. And the grand mean is just like the mean of those 3 means. It's just that simple. We add those 3 means together and divide by the number of groups. Then we do an estimating of EVAR for those means. So we imagine those as our 3 in our sample. If we have 3 groups, then we have 3 means. And we're going to go through the process of calculating the squared deviations, calculating the sum of squares, and then calculating EVAR for those means, dividing SS by the number of groups minus 1, or SS by DF groups. And then we just multiply that figure, the EVAR means, by the number of individuals in the sample. And that brings us to our, that second, the top, the numerator of our F ratio. So this is the calculation example for the between groups variance. MS between, or here I'm calling it EVAR between. We can see we have the 3 means listed here. The mean for group 1, those people who saw that the defendant had a criminal record, the mean for group 2, who saw that she had no criminal record, and the mean for group 3, who were told nothing about her criminal record. So we've calculated then the number of groups. We have 3. The DF between is 2. The grand mean is the average of these 3 means, 5.6677. We calculate the sum of squares by taking each score and subtracting the grand mean, and then squaring it. And when we sum these squared deviations, we get our SS, our sum of squares, just like before. Our estimated variance is still as it was, SS divided by DF, and so that gives us our EVAR, which in this case is the EVAR for the means. So I've written this here so we're clear on what this EVAR is representing, 4.33. And then the last thing we do is we multiply it by the number in each group. And so in this case, we have 5 in each group. So we take this EVAR means, multiply it by 5. That gives us our EVAR between. That's what we use in our formula. And so when we calculate the F ratio, we're going to take MS between and divide by MS within. And remember, we can also say EVAR between, EVAR within. We'll see which way we decide to go, and then we'll stick with it. And so we'll get this 21.6667 divided by 5.33, which gives us 4.0625, and this is the ratio that we will use to determine whether we have a statistically significant result. We'll go through lots of examples on paper and in the spreadsheet, so this process will become more clear. Finally, we're going to decide and conclude. So here we can see that our F-score is 4.0625. I've gone ahead and plotted it, and we can see that it falls within this reject region. So we'll make the decision to reject the null. Now remember, our null hypothesis just stated that the groups were equal. That's all we can conclude here. And so we write our conclusion like this: jurors' decisions about guilt of a defendant differ across the three conditions. And we put our statistic like this. We write the statistic, which is F. We write the number, the DF between, comma, DF within. We put that statistic that we just calculated using 2 digits, and then we tell our probability level. Now, note that we didn't state which groups was higher. It seems pretty obvious that our group that had 8 was going to be higher, but we don't know that from this test. All we know is that the variance between the groups is greater than what we would expect if the groups weren't different. It's greater than what's explained by the variance within the groups. That's all we know. And so in order to do anything more, we actually have to do some post hoc testing. So the post hoc testing we'll have in a separate lecture, and that will help us determine which of the 3 groups were significantly different.